This part, we're going to find two things. We're going to find the expectation value of the momentum squared, and we're also going to find the expectation value of the kinetic energy for the nth arbitrary state of the quantum simple harmonic oscillator. It's quite a mouthful, but we'll go ahead and get started on this one. So, of course, with the expectation value, we're going to integrate over all space and then sandwich that momentum squared operator between the complex conjugate of the wave function and the wave function of the nth arbitrary state. And so the momentum squared operator is equal to this. And if you're confused on where this came from, it was explained in the textbook, and if you're confused, I'd recommend going back and reading that section, but here it is right now. Okay, now as you can see, we're going to go ahead and first things first is pull out the constants out in the front here, and then distribute this nth arbitrary wave function to all these different linear combinations. And again, for the sake of time, I'm just going to write an indefinite integral, but just know that it's actually an integral over all space. Whoops, that's okay. We have erasers. Oops. Mistakes are fine as long as you can catch them. You learn from them. Okay, that looks pretty good. Now in this step, we're going to go ahead and evaluate each and every one of these operations. In the previous part of this problem, I went explicitly into this. But so we'll just go ahead and just jump into it. So we know that the raising operator acting on some nth arbitrary wave function is going to create some constant, which isn't necessarily important right now, but is important, but also raise that wave function up 2 states, so the n plus 2 state. And the same thing goes with this one, which is, again, oops, another mistake, but that's okay, we caught it. We know exactly what we're looking for. This one will be some constant, but it will lower it down 2 states, so n minus 2. Now, these are the ones that we need to concentrate on right here. So we know this is equal to the raising operator acting on this right here, which was explained in the textbook and the previous part of the problem, which would be the state it was previously at, and then the state lowered by 1. And then when this moves through this constant here and operates on the wave function, that'll raise it back up to the nth state, and then it'll pop out another constant, and for the raising operator, it's equal to the new level that it's actually at. And so we just do it in the opposite order here. The raising operator acts on the wave function and gives us the higher state, and then pops out a constant equal to the new state. And then the lowering operator lowers it again back down to the nth state, and then multiplies it by the previous state it was just lowered from, which would be this one right here. Okay, and we can go ahead and write all these out. Well, actually, before we do that, I think I want to make it explicitly clear that whenever you do an integral over all space of an overlap of 2 different states here, nmm dx over all space, let's go ahead and move that down just a little bit. That could equal 2 things, either 0 or 1. It equals 1 when n is equal to m, whenever it's the same state, or it's equal to 0 when n does not equal m. So as you can see here, we have these different states. We have these different states right here, but then we have this end state. So we expect all these terms here to be 0. And then these terms here will be 1 once the integral and the space kind of move on to each and every one of these linear combinations here. And again, if this seems like too big of a jump, I did it explicitly in the last part of the problem, the previous video, and it's also covered in the textbook. But So we'll go ahead and just go ahead and apply those integrals and evaluate them. They're either going to be 1 or 0. Let's scroll up a little bit. All right, so this is relatively simple to solve. We'll go ahead and distribute this negative sign into here. So that leaves us a plus sign here. And then we have h bar, times 2n plus 1. Okay, so that's the momentum squared operator. We can go ahead and use that for the next part of the problem, which is the kinetic energy expectation value. So the kinetic energy expectation value, this is a lot faster to find. If we think about it in terms of classical mechanics and in terms of momentum, it would just be 1/2 1 over m times the momentum squared. But since we're talking about expectation values, we're going to use the expectation value here. And luckily, we just happen to solve for that momentum squared value right here. So we can go ahead and put it in. Relatively easy algebra problem to solve. We'll go ahead and take care of our bookkeeping. And we can go ahead and, let's see here, let's pull the h bar omega out here and then distribute this 2 into here. One half. Okay, let's go ahead and distribute that 2. That 2 will act on the 1/2, or the 2, we get an n, and then we'll get a 1/2 here. And this is important. This is going to be show the relations that we're going to get for the different energies later on in the problem. But for now, right now, we are done finding the kinetic energy expectation value and the momentum squared expectation value.